It's beautiful. It's definitely a nerd talking. So we're talking about parametric equations. You should have seen these in pre-cal. You should have seen these in pre-cal. If you didn't, it's not a big deal if you didn't, because they're pretty simple. So I'm saying you have seen parametric equations before, okay? Whether you believe it or not. And there's a way to graph parametric equations on your calculator. I'll do that today for sure. Because if I give you one, and it's pretty rare that I give you one on the exam, you would want to graph it, okay? It would be more for the arc length than it would be for the area. So there's a couple of parametric equation problems in the area section, but I never give one of those on the test, okay? So parametric equations, right, usually we would see something like what, x squared plus y squared equals 1, right? This is the equation of a circle, right, of radius 1. And so you would see it more as y equals plus or minus square root of 1 minus x squared, right, where the positive piece is the upper half and the negative piece is that lower half, right? So, but this is a nice one to write as a parametric equation, and this one turns out to be x equals cos of theta, y equals sine of theta. So this one is a function of x, right? Or an explicit equation, right? You've heard of implicit differentiation, explicit differentiation in Calc 1. So this is our explicit function of x, and these are my parametrics. So you see I have x and y defined again, but based on a third variable, my parameter theta, right? And so this is what we mean by parametric equations. So it's kind of interesting to see this as the same curve here, but I'll show you, and I'll use Desmos just because it's a lot quicker. Okay, so I'm just going to Desmos here. So this is kind of nice to have a break like this from all of this content we're learning, because there's nothing to do here with these parametrics. You just got to plug them into our formulas. When I write a parametric on Desmos, I put it as a coordinate. So x was cos of theta, right? So I'll use cos of t, comma sine of t, instead of writing out theta. And so you can see it's starting my circle here. From 0 to 1, it's starting my circle. If I go to 0 to 3.14, right, 3.14, you see a half of my circle, right? And then if I go all the way to 2 pi, you can see the whole circle, right? And I should be able to do this as, can I? Nope. But the whole key is I'm seeing, and we usually use t for time, so I can see that circle being drawn out in time, right? That's the idea. Whereas if I just plot the full equation, it just gives me the whole equation. So this thing is kind of allowing me to do this by time. I thought I could control this a little bit better. Oh, I know how. I'm going to call this A and add slider A. So I'm going to pick A to go from 0 to 2 pi. And so now you can see that circle drawing out in time. And so this is the nice piece about this parametric equation, is we're usually talking about a particle moving, right? If we're engineers, we're talking about a ship moving along a path, right? We have to be along the right curve to break through the atmosphere and not bounce off back into space, kind of thing. So, right, we're kind of watching the shuttle come back to the Earth at the right angle to get through the Earth's atmosphere, um, uh, kind of thing. So these parametric equations are real valuable. We can kind of predict the future path. Where is it going to hit? What angle is it going to hit? That type of thing, and then make adjustments, right, to the trajectory with thrusters and things like that, like all those space movies. It's cool shit, but I mean stuff. Oops. So you've seen a parametric equation before, am I right? Have you seen this before? This particular piece I'm talking about, that x equals cos theta, y equals sine theta. And typically anybody see these in pre-cal? Tell me, just somebody lie to me and say yes.
Yes, I remember.
Thank you. Thank you. I don't think you're lying either. I think you actually did say it. But they get really cool so normally it's x equals r cos theta, right? So the radius, I can adjust that radius by putting in a 1 there, putting in a 4 there, and y equals r sine theta. What really gets cool is if we take that radius and put something in it, like if we do x equals theta cos theta, or y equals theta cos theta, the sine theta, right? If I change that radius to variable, it gets pretty cool too. I'll do that real quick. So t cos t, it's t sine t. Oops. And you see I'm going to get a spiral, right? So as that radius starts at 0, gets bigger and bigger and bigger and bigger, I get this spiral. And so so with these parametric equations, notice that my x-coordinate is a function, right? T cos t, that's a function, passes the vertical line test. My y-coordinate is a function, passes the vertical line test. But my overall curve is not. It fails the vertical line test. So we can start doing these crazy curves now with functions, whereas before we couldn't. So this is one of the beautiful things about, and we get real nice ones if we put in like cos of t times cos of t. Oh, it doesn't like it. No, it doesn't like my curve for some reason. But you can get some really beautiful curves out of these parametrics. Not the one I just did, of course. So the whole idea is that you could eliminate these, right? Right. If I square both sides here and add them together, I get x squared plus y squared equals r squared, right? So these parameters can get eliminated to get back to the world we're used to, as opposed to this parametric world. So one of the things that we do is we can trick things to be parametric. So for example, if y equals the square root of 1 minus x squared, and I say x equals t, then notice what happens here. I get y equals square root of 1 minus t squared. So even though I started with a function that's perfectly normal, I can turn it into parametrics. I can turn it into parametrics by doing this little cheap switch, okay? But sometimes I cannot. Sometimes I cannot eliminate the variable. But this is a key, as any explicit function of x, right, f of x equals y, can be made into a parametric equation and it's a cheap version, okay, with x equals t and y equals f of t. So just by renaming the variable t, I can plug it into this situation where I have I can kind of cheat the parametric idea, where I can graph out a square root of x function in time, right? So put in a new parameter. So let me do that one on Desmos real quick. T comma square root of t, right? And I'm going to let t go from 0 to a, and I'm going to add my slider a, and you can see here, as I move this to the right, you can see my curve being drawn out in time, right? So as opposed to just graph the whole curve at once. And so, and again, this is useful in space flight and all kinds of controlling robots and your vacuum cleaner. If anyone has the vacuum cleaner, that I have one of those and they suck. Get it? The vacuum cleaner sucks. Get it? I know it's not funny. Thank you, Angel. Thank you for humoring me. So if we look at section 6.1, there's some nice parametrics in here. And so I had originally assigned some problems from 6.1 in MindTap. I think they were 33 to 38, but I'll just look at 37 for now. So I do like those in MindTap for the parametrics. And but 37, number 37, it says that x equals t squared and y equals t cubed minus 3t. So in this particular one, it's not that easy for me to eliminate the variable t. In this one I can. It's not pretty, that's for sure. But obviously, if x is t squared, then x is square root of x is t, right? So this is just me working on eliminating. And I've got y equals t times t squared minus 3. So I've got y equals square root of x times x minus 3. So there I've eliminated the variable. So I can change back from my parametric world back to my explicit function of x world, right? But you don't have to do that. They're not asking you to do that, but it's going to be a key when you see me do a couple of things later. So on this one, I'm gonna graph this on Desmos. I should use the calculator. Anyone have their calculator here today?
Yes.
Okay, so let's use our calculators here because again, I usually don't put an area problem with the calculator on the test. Sometimes I put the arc length. I didn't do arc length last semester, so in the midterm it's not on there. So anyway, but I've got my calculator open. Please control me. Right? If I'm going too fast, stop me. If you need me to repeat something, let me know. I go into mode, the mode button right here, and I see the types of functions I have. I have a function, I have parametric, I have polar, and I have sequences. Right? So we're going to change to parametric. So we go down to function over to the right and hit enter. So now I'm on the parametric setup. Okay, how are we doing? Are we okay? So Angel had a calculator. Who else had a calculator for me, just so I know? David, Eleanor, thank you. Sarana, Ash, Jerusalem. You're all going along with me here. Adam, Charlene. Almost everybody's got their calculator today. Awesome. But don't let me run you over. If I have to repeat something, I'm okay with that. Okay. I'm going to press the y equal button, and normally it would say y1, right, for the first function of y, and then y2 for the second function of y. Now it says x1 sub t, y1 sub t. So I'm creating some x and y coordinate, right, using that variable t. So I had x is equal to t squared, and I had y is equal to t cubed minus 3t. So I'm just putting all of that in. Now, typically, I don't know where t is going. I don't know what this thing looks like. So so what I will do is I will just let t go into the positive direction in C. And then maybe I'll let t go in the negative direction as well. So it's really, I'm kind of playing around with this at first because I don't know what things look like. Okay. So, but I want to just graph this. So I just go to graph. Is everybody here? Anybody need a minute, or everyone's okay? Okay, good, Ash, thanks. So I'm just going to hit graph, and you can see it curved out that first bit of mine, and I can almost count. I can almost see. I can see the time passing, right? 0, 1, 2, 3, 4, 5, kind of thing, right? And that's my variable t. So my x-coordinate is moving by t squared. So when t is 1 second, 1 times 1 is 1, x is 1. When t is 2 seconds, 2 times 2, remember x is t squared, 2 times 2 is 4. So I'm all the way at x is 4. Where I'm at with the height depends on the y-coordinate. So, but I want to go into window, and notice here it says that's starting at 0 and ending at pi, right? Do you see that? Starting at 0, ending at pi. So, but maybe I want something different. So let me start at -10 and end at 10 and see what happens. And then I go back to graph. Ah. So I was missing part of my curve. Right? Just doing the positive time values, I was missing part of the curve. And of course it doesn't make a lot of sense to talk about negative time. So but t here is our variable, and because of these symmetries in some of the curves, we're going to want to let t start at negatives. Does everybody see the same curve on their page, on their calculator? Nice. So some cool things. When I first started seeing this stuff as a student, I was like, oh my god, I'm going to get the computer to write in cursive. Didn't last long. I gave up on that one pretty quick, but just kind of inspired to see all the shapes that you can make. And so we're finally ready to talk about how do I get area, and it's pretty clear where I'd want the area here, right? Looking at this curve, where do I want the area?
In the loop.
In the loop, exactly. I want to see how big that loop area is, right? So the idea is for area, we know how to get area. The area, it goes from a to b, right, of f of x dx, right, or g of y dy, right, or c to d of g of y dy, right? We already learned that in Calc 1, right? Now, in Calc 2, we've got these area between curves, but we're gonna use our parametrics to go back to this Calc 1 piece and see what happens. So what did I had? I had x equals t squared, right? And I had y equals t cubed minus 3t. So what do you think? So this is clearly this one, right? It's clearly this one. Right? Yes, you agree, because y is my independent. I'm sorry, x is my independent, right? X is the independent and y is the dependent. And it's f of x. It's already, so this is really what? This is my area equals a to b of y dx. And so you can see I can fill in here, right? So what am I going to get, though? I'm going to get the integral of alpha to beta. Okay, what's that? That's the key. This is going to be where my loop starts and ends. So the alpha and beta are going to be where my loop starts and ends. And then y is what it is. It's t cubed minus 3t. But what's dx? What's dx for me?
2x.
Almost.
2x dx right? 2x dt. Yeah.
Yes, 2t dt. Yes. 2t dt. That's how simple this area piece is for these parametrics. I still need to figure out alpha and beta, and maybe I can distribute my my pieces here. What do I have? 2t to the fourth minus 6t squared, right? I still need to figure out my alpha and beta. So how do I figure out my alpha and beta? Well, if you look at it, if you look at my curve, where's my loop starting and ending, right? In this particular case, it's when y is 0, right? So I have to just do a little bit of CSI mathematics version, right? Crime Scene International mathematics version, right? There's a problem on the board, the teacher's dead on the floor, chalk dust everywhere, right? You gotta investigate and figure out what's going on. So I see that y is equal to 0. So t cubed minus 3t equals 0. So t times t squared minus 3 equals 0. So t equals 0, and that's over here, right? That's over here. That's not that interesting to me. Or t equals plus or minus square root of 3. And that's where I need my pieces, plus or minus square root of 3. So my area is finally going to be minus rad 3 to rad 3 of 2t to the fourth minus 6t squared dt. And I think, David, this is actually might be identical to the problem on WebAssign. I think it's really close to it. But maybe the loop is different, but we'll just have to figure out where the loop begins and ends. Now, I could do symmetries here, right? Do you agree? If I start, if you remember where I had, if I started from, I certainly can start from minus rad 3 to 0 and get this top area, or I could start from 0 to rad 3 and get the bottom area. But I'll let you play around with that. We can just go with this, right? We got 2t to the fifth over 5 minus 6t cubed over 3, evaluated rad 3 minus rad 3. And you can see why I wouldn't put this one on the test. I don't care about definite integrals. I care that you can do the integrals. I don't care if you can plug numbers into the integrals after you do them. Right? Does that make sense? What I'm getting at there? I don't really care about. And I'm just noticing I've got
Could you explain again the relationship between x and t?
yes. So x is getting, the x coordinate is moving along the x-axis based on this parameter t, right? So in this particular case, if x equals t squared, right? If t is 0, x is 0. T is 1, x is 1. If t is 2, x is 4, right? So I'm kind of building up my x coordinates here with time. But y is also based on t, right? So when I plug in t is 0 for y, and what is y again? Y equals t cubed minus 3t, I get 0 again. So now I've actually got a point on my curve, 0, 0, based on time t, right? At time t, I got an x coordinate of 0, y coordinate of 0. I plot that at 0, 0. At 1, when I plug in 1 here, I get a negative 2. So at 1, I get a height of negative 2. So when t is 1 for the x coordinate, I got an x coordinate of 1. But when t is 1 for the y coordinate, I got a y is negative 2. So I plot the point 1, negative 2. I plot the xy at time t. And so it's creating that that loop, right? That top half of the loop for me.
Okay, thank you.
Yep. So anyway, this is it. That's how easy it is to get area inside of a parametric curve, right? And that's that other piece of 6.1 that I did. Let me look at one problem on WebAssign there, and then we'll move on to 6.4. So let me open WebAssign, which I never do this because I hate WebAssign. We'll be done with WebAssign in one more year, but you'll be long gone, so you don't care. So I'm going into that homework 9, area between curves. Oh, I should have hit view. Sorry, I keep forgetting I'm in as an instructor instead of a student. And so I think, so the first one is area between two curves, top minus bottom, right? The second one is right minus left. The third one is parametric, and the fourth one is not parametric, right? So, but it's the third one that's parametric. So let's take a look at that one together. Now notice my 2 there is red. When you see the red numbers, they're different. So you could have a 2, someone else could have a 3, someone else could have a -5, that type of thing. So not everyone always has the same questions, which is why I'm asking you to send me pictures off a website, right? So, but I'll do this one, x equals 2 plus e to the t. So this is homework 9. Number 3. And I've got x equals 2 plus e to the t, and y equals, don't tell me, t minus t squared. Now, because I have to figure out alpha and beta, I have to figure out where if there's a loop and when the loop starts. I want to get a nice picture of this. If I'm doing homework, I'm doing it on Desmos most likely. Make sure you do 1 at least on your calculator. But I'm telling you, I don't have a lot of room for this stuff on the test. So 2 plus e to the t, comma, T minus T squared, is that right? T minus T squared. That's such a horrible memory. And it looks like I just have this little bump here in the ground. I want to make sure I like doing things like minus 10 to 10. So that shows me a little bit more for sure. And then that shows me more. And you can see I simply want the area under the curve there. So when my curve is underground, I'm going to get negative area. When my curve is above the ground, I'm going to get positive area. If I have some curve that goes above and below, whatever's bigger is going to give me the result. If there's more area underground, I'm going to get negative. If there's more area above ground, I'm going to get positive. But it looks like I want that area in that little piece above ground. Is everybody with me there? And I better read the directions, because that's what I always say the issue is. We don't like to read. Well, at least I don't. What do my directions say? Find the area enclosed by the x-axis in the given curve. So find the area above ground, right? So it's pretty clear that I have to find when does the curve hit the ground. And so what do you want to think about? When does the curve hit the ground? What do you think? How do we think about that? When does the curve hit the ground? What variable should we use? Should we use the x or should we use the y?
Y.
Yep, the y is 0, right? When it hits the ground, its y is 0. So I'm trying to say, okay, if y equals 0, that means t minus t squared equals 0, or t times 1 minus t equals 0. So t equals 0 and t equals 1, right? So there's my alpha and beta. So I'm getting the area from 0 to 1 of y dx, right? And my y is t minus t squared, and my dx is e to the t dt. Make sure you agree with me. Make sure you get the derivative there of 2 plus e to the t. Oh, this one's cool. This is,
what does the 0 and the 1 signify?
yeah, the time when time
On the graph?
yeah, when at what time does the graph hit the x-axis?
Okay.
So this is nice. This is a by parts, and this is a tic-tac-toe, right? So let's do this one. I need sine plus minus plus minus. I need my u, which is t minus t squared, and I need my dv, or v, which is e to the t, right? That's e to the t every time. So what's my first derivative there? I get 1 minus 2t, and then I get negative 2, and then I get 0. I'm doing your homework for you. I'm sorry about that, but you know, you'll have a slightly different problem, slightly different alpha and beta, a different area, maybe, right? So it looks like I got t minus t squared e to the t plus 2t minus 1 e to the t minus 2 e to the t evaluated at 1 and 0. And I might be doing that quick, I'm sorry, but you don't have to follow me. You do it on your own, right? And let's just make sure we get to the same place. Oh my God, isn't this a nice break from what we've been doing? This is easy. Need a break every now and then, us humans. I like to factor out the e to the t. And then see what happens. So e to the t. And when I evaluate at 1, and then evaluate at 0, we get 3 minus e. Let me know if anyone else got there. Eleanor, yes? Nice. Angel's there, great.
Can you explain what happened to the T?
Yeah, so but,
On the third to last part?
yeah, so I'm plugging in 1 for t and then 0 for t. Right? When I'm evaluating, I'm plugging in 1 for the t. Let me put lines on, Josh, okay? Let me put numbers on, okay? Sorry. Where are you at there?
Oh, so did you plug in the 1 into the E at the beginning of, what is it, 8?
Yeah, exactly. I plugged 1 in here, 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 and here to get this piece.
Right, okay.
And then it plugged in 0 in to get this piece. And then you subtract the 2 pieces.
Alright, got it.
Yep. Well, I'm looking at the time, and I'm going, oh my God, there's no way I'm going to get 6-4 done. I want to start it today, but I won't get it done, but that's okay. Okay. But we'll do as much as we can, and I'll finish it for sure tomorrow. Let me stop my recording because we're done with this parametric introduction to parametrics and area under the curve with parametrics. So let me just stop this recording here.